chapter 8. Let's talk about chapter 8 first and review some of the concepts real quick that were in chapter 8. Remember, we learned about the empirical versus the molecular formula, right? Chapter 8's been like the last time we did the first part of chapter 8 was before Christmas, right? So it's been a while since we've thought about this stuff. You guys remember empirical versus molecular formula? Is this an empirical or molecular formula? That's molecular. Why?
Because it hasn't been.
It can be divided by 2.
It can be simplified further as far as the ratio between the various elements in it, right? If the numbers that are here can all be divided by a common factor, then it's not the empirical formula. So if we divide everything by 2, that tells us that the empirical formula would be that, right? But if I have a formula like this, is that formula an empirical formula? Yes, it is, right? It's already in its simplest form. There's no common factor I can divide everything by, except for 1. That's also the molecular formula for H2O, right? That's the way the molecule actually appears in nature, but it's also, for this one, the molecular formula turns out to be the empirical formula as well. So everybody understand the difference between molecular and empirical? Yep. All right. What about calcium hydroxide? So you remember your chart of polyatomic ions. One of the things that you were supposed to do that was going to be on one of the quizzes, and it was going to be on the test too, was you were supposed to memorize those 7 polyatomic ions, right? Well, I'm giving you a break. You only have to memorize these 2 for the test, okay? Those are the 2 that will be on the test. So make sure you know sulfate and make sure you know phosphate. So if I give you a problem, like I say, give me the chemical formula for magnesium sulfate, you should be able to do that. So we'll do an example here with calcium hydroxide, which was one of the other ones that we learned. Does anybody remember what calcium hydroxide is, the formula for it and the charge?
OH with a negative.
OH negative, that's right. OH negative, right? So how do we go about figuring this out? Well, first, this is an ionic compound that's comprised of the calcium ion and the hydroxide polyatomic ion. And so we look in the book and we see that calcium is in column 2 in the periodic table, right? So Ca is going to have a 2+ charge. It's a metal that's going to donate, two of its electrons to this polyatomic ion, right? OH, we memorize to be OH negative. So it has a 1 negative charge. And so what do we do now? We swap and drop. Remember that? And so when we swap and drop, the Ca gets a 1, which is understood. We don't write that down. The OH is going to get a 2. But since the 2 needs to apply to the entire polyatomic ion, you've got to put a parenthesis around that and do the 2 like that. Does that make sense to everybody? Yes?
I thought you would only put the parentheses around it if there was already a number in front of the OH.
No, because if I don't put the parentheses there, it looks like that 2 only applies to the H. Right? And so we have to make sure that we know that the 2 applies to both of those. Okay, so with or without a number. That's a good point, though. You need the parentheses around the polyatomic ion. The only time we don't have to put it is if there's not a number here. Like if it's an understood 1, then we can leave the parentheses on. Okay? Like if this was, instead of if it was KOH, if it was K has a +1 charge, OH has a negative charge, and so when we swap and drop there, there's an understood 1 here, and there's an understood 1 after both of those, but we don't need to put it because it's understood. Okay? All right, any questions about those? What if I gave it to you, never mind, I already said calcium hydroxide. Okay, so I could ask it the other way and say, give me the name. I could ask you that. Let's go over real quick example 8.1. Just kind of reviewing that concept. Like I said, that last time we worked that in class was at the end of the year, end of 2020. So example 8.1 says that a chemist makes hydrogen gas according to this equation. Zn solid plus 2 HCl aqueous. That yields ZnCl2 aqueous plus H2 as a gas. And it says the chemist uses an excess of zinc and 150 grams of HCl. So we've got 150 grams of this. When she collects the hydrogen gas, she finds that she made 3.9 grams of it. So the hydrogen gas, she got 3.9 grams of this. What is her percent yield? So this is a question about percent yield. Do you guys remember what the definition of percent yield is?
It's the actual yield divided by the theoretical yield.
So it equals actual divided by theoretical, right? And then to get the percentage, we multiply that times 100, times 100%, right? So Cruz is exactly right. So in order to do this problem, we know that we produced 3.9 grams. That was what the actual production of hydrogen gas was, but we got to see what should we have produced if, theoretically, if everything was perfect, using 150 grams of hydrochloric acid. So how do we determine that? Well, we got to figure out how much hydrogen gas we should have produced, right? So the way we do that is we first take this and convert it to moles, right? So 150 grams of HCl converted to moles. 1 mole of HCl is equal to how many grams? The way that we figure that out is we look at the atomic mass, right? HCl has an atomic mass of 1.01 plus, what's Cl? I never can remember.
I think it's 35.45.
Is that the 35.4? Yep, 35.45. Oops, 35.45. And so that's going to equal 36.46. And that's 36.46 grams per mole, right? If it's that many atomic mass units, then that means for 1 mole of that, we have that many grams. So we're going to write 36.46 grams of that here. And we get 4.114 moles of hydrochloric acid. So if we have that many moles of hydrochloric acid, 4.114 moles, how many moles of H2 should be produced? And the way that we figure that out is using stoichiometry. 4.114 moles of HCl. We know that for every 1 mole of H2, we have 2 moles of HCl. So basically be half that. And so that is 2.057 of H2. We're almost done. That's how many moles should have been produced, but we need to know how many grams should have been produced. So now we use the atomic mass of H2, which is 2 times 1.01, or 2.02 grams per mole. So we'll just multiply this times this. We know that for every we know that for every, I'm just going to do it like I normally write it. For every 1 mole of H2, we have 2.02 grams of H2. So that gives us 4.16 grams of H2. That's what should have been produced in a perfect world. That's the theoretical yield, right? But what was actually produced was 3.9 grams. And so the percent yield then is just actual, which is 3.9 grams, over theoretical, which is 4.16 grams, times 100. And so the percent yield was 94%. Did everybody follow that? This should have been old stuff here, right? Going from grams to moles and then figure out the moles of the other one. That's all the stoichiometric calculations that we learned when we first got into stoichiometry. We went from grams of one substance to grams of the other substance, right? It's the old grams, moles, then from to moles to grams. We just did that. And then we plugged it into percent yield formula. Okay. So let's see. Percent yield, I just talked about that. 8.4. What is problem 8.4? Problem 8.4, this is probably where we're trying to figure out the empirical formula. Yeah. So a chemist burns 50 grams of an unknown substance containing only carbon and hydrogen in a combustion analysis experiment. So we burned 50 grams of some substance. We don't know what it was, right? But what we do know is that it only contained carbon and hydrogen. And when we did the experiment, when we combusted it in this contained environment so that all that we introduced to the equation was oxygen. So we basically combined this unknown substance with oxygen. This is what we collected. We got 146.4 grams of CO2, and we got 89.9 grams of water, 89.9 grams of H2O. So the question is, what's the empirical formula of this unknown substance that only contains carbon and hydrogen? So it's probably been a while since you've thought about this one too, unless you've already been studying this stuff. And if you have, then you're good. This will be a review and you can answer all the questions and I won't have to do anything. So what do we need to figure out? We need to basically figure out, if we're talking about the empirical formula, we need to figure out the number of moles of the carbon and the hydrogen. And if we can calculate the number of moles, then we can see what the relationship is between the two and figure out what the empirical formula is, because that's what the empirical formula tells us. Remember that. It's the simple ratio of all of the atoms in the compound, right? So for every carbon atom, there's this many hydrogen atoms, or vice versa. So that's what we're trying to figure out. And we do that by getting the number of moles of each. So let's start with 146.4 grams of CO2, and let's convert that to moles. CO2 is, C is, what is C? 12.01. 12.01 plus 2 times 16. So for carbon dioxide, it's 44.01. 44.01 grams per mole. And so we put 1 mole on top here, 44.01 grams on the bottom there. And so how many moles of carbon dioxide do we have? We have 3.327. CO2. All right, let's do the same thing for H2O. We know we had 89 grams of H2O, 89.9 grams of H2O. And for H2O over here, we calculate this to be 2 times 1.01 plus 16. And so that gives us 18.02 grams per mole. 18 grams for every mole. So 1 mole of H2O is equal to 18.02 grams. So we do that calculation and we get 4.99 moles. All right. Now, what elements are in our unknown substance? There's only 2 elements in it. What?
Carbon and hydrogen.
Carbon and hydrogen. Right. Carbon and hydrogen is the only thing in our unknown element. So this told us the number of moles of carbon dioxide, and this told us the number of moles of H2O. But we're interested in the number of moles of carbon and the number of moles of hydrogen, because that's all that's in our unknown substance. All right? So this is an area that sometimes students get confused in, so I want to make this clear. If I have 3 CO2 molecules, all right, so I got a C with a couple of O's hanging off of it, right? I've got 3 of those. So if I've got 3 of these, how many carbons do I have? Just carbon atoms.
3.
I have 3, but how many oxygen atoms do I have?
6.
I have 6, right? So what if I had 3 moles of CO2? How many carbon atoms would I have?
3 moles.
3 moles, because remember, mole is just a number that designates a quantity, just like the word dozen does, right? So if I have 3 moles of CO2, then I have 3 moles of carbon, and I have 6 moles of oxygen. Does that make sense to everybody? Okay? And so what that means then, for this problem here, since I have 3.327 moles of CO2, then I actually have 3.327 moles of just carbon. But for this one down here, since I have 4.99 moles of H2O, then I'm going to have twice as many hydrogen atoms as that, right? So I'm going to have, what is that, like 9.98? 9.98 moles of hydrogen, because there's 2 hydrogen atoms in this molecule. So it's 4.99 times 2. Did that make sense to everybody? All right, so now that we know the moles of carbon and the moles of hydrogen, we can figure out what the ratio is between those two. So you put the bigger number on top, 9.98 moles of hydrogen divided by 3.327 moles of carbon. So that's going to basically equal 3. All right, 3.00. That's the ratio of hydrogen to carbon atoms. We put the number of hydrogen on top and the number of carbon atoms on the bottom. So there's 3 times as many hydrogen atoms as there are carbon atoms, right? So our empirical formula would be CH3, and that would be our final answer. Okay? Like I said, I just know it's been a while since we've looked at this stuff. And I wanted to do one problem just to give you an opportunity to ask questions if any of that was confusing. So, yes?
Why was the 3 added to the end of CH? Not like in the front of it or in between that?
This?
Yeah.
Because we figured out the ratio of hydrogen atoms to carbon atoms. Just like here, the ratio of oxygen atoms to carbon atoms is that for every 1 carbon atom, there are 2 oxygen atoms, right? 1 C, 2 O's, CO2. Well, here, what this calculation here told us is that for every 1 carbon atom, we have 3 hydrogen atoms. And so we added the 3 after the hydrogen because we have 3 hydrogens for every 1 carbon. And the reason that we know it's that way is because we put the bigger number on top, which was the hydrogen. There's more hydrogen, more moles of hydrogen than there is carbon. Okay? And so how much more? Well, doing this calculation here tells us there's 3 times more hydrogens than there are carbons. Does that make sense? All right. So we've already done percent yield. There's a problem on page 255 that I really wanted to do, but we're running short on time. It was number 16, where they ask us about the, we have a 500 gram sample of an unknown substance that's decomposed into a certain number of grams of magnesium and carbon and some oxygen that couldn't be measured, but that's okay. So we can calculate the oxygen because we know the total mass of it was 500 grams, so we know how many grams of oxygen that was. And it's basically an exercise in doing the same thing that we did here. It's just in this particular one, it's not just comprised of only carbon and hydrogen. It's comprised of, it's not just comprised of 2 elements, it's comprised of magnesium, carbon, and oxygen. And so you take the grams that are there, you use the atomic mass to convert each of those to moles, and then you take whatever the smaller number is and you divide the bigger numbers by the smaller one and you figure out those ratios and you do exactly the same thing. Okay? So it's the same type of problem, it's just presented a little differently, and I wanted to make sure that y'all understood that. But you should be able to. That's in the review. So I would recommend, looking at your, you should have everybody should have the answer key and test book. That was one of the things required for the class, and that's got the review worked out for you, and so you should be able to look at it in there and figure that problem out. All right, let's talk about chapter 9 real quick. We talked about the effect in chapter 9 of pressure and temperature on solubility. And so if I have a gaseous solute, so a gas that I'm dissolving into something else, and I increase the pressure, does the solubility of that gas increase or decrease?
Increases?
It increases. And the way that I think about that is a can of Coke, right? It's under pressure, and while it's under pressure, the bubbles stay in there. But as soon as I pop the top on that, you hear psh, all of a sudden gas is already escaping from the solution, right? So when the pressure goes down, then it becomes less soluble. It's not staying dissolved. Some of the gas is escaping. For solid, if I increase the temperature, if I have a solid solute and I increase the temperature, does the solubility of the solid solute go up or down? Huh? Up? It goes up, right? A solid solute solubility increases when temperature increases. And the way that I think about that is your sugar in your tea, right? It dissolves well in hot tea, doesn't dissolve so well in cold tea, right? So when you heat it up, the solubility increases. What about a gaseous solute? Does its solubility increase or decrease when the temperature increases?
Decreases.
It decreases, right? A hot Coke will lose its fizz quicker than a Coke that you stick in the fridge. It all comes back to drinks for some reason. I don't know. Soft drinks and tea. All right, so very good. You got that down. Let's ask about molarity versus molality. What is the formula for molarity?
It's moles over kilograms?
Its molarity is moles of the solute over liters of solution. So you were giving me molality
is moles over kilograms.
of solution. And then molality, which is a little m, is moles of solute over kilograms of solvent. All right? So make sure you know the distinction between those two. Recognize that both of them contain moles of solute. So there's kind of sneaky ways that I could make you do stoichiometry, right? By giving you the molarity or giving you molality, and you have to calculate the moles from that, and then you have to do some stoichiometric calculation. So just make sure that you understand how to use those formulas and understand the problems that use those. And then finally, freezing point depression and boiling point elevation, right? So we've got two equations that you have to remember for that. They both have to do with change in temperature. So the freezing point depression equation is what? Change in T equals
Negative I KF.
Lowercase m.
lowercase m. I like Kentucky Fried molality. Maybe. Kentucky Fried moles. You can say that. But it's not really moles, it's molality, right? So that's the freezing point depression equation. What about the boiling point depression? What about the boiling point elevation equation? It's also change in T. But it's what? I, K, B. Who said that? Okay, I, K, B, M. I can't do Kentucky Fried on that one, so I don't know. I kick beautiful moles. I don't know. That's just what I do. It's a habit of mine, right? But this one's negative because it's the freezing point depression. The freezing point goes down. The boiling point elevation, it goes up. So this is a positive number, whereas this is a negative number. And the only thing you have to remember here is what does I signify?
The number of ions or molecules.
Number of ions or molecules. So if it's an ionic compound, if it's like, for example, NaCl, right, this splits into two ions, Na and Cl, so I would be 2 for that one, right? But if it was like the one that we did earlier where you had, what was it we calculated, CaOH2, right? That splits into 3 because you got the Ca ion and then you got 2 OH ions. And so it'll be 3 for that one. So make sure you know how to do I, and then the only other thing you got to remember here is that when you figure out change in T, if I were to ask you what's the new boiling point, you'd have to take this value and have to add it to 100 degrees Celsius because the boiling point has changed to that. Yes?
Let's say inside of the parentheses there was a 3, for example. How many ions would there be in that?
Okay, because this is, so it would be kind of like one of these guys. Let's say, for example, SO4, let's say it was SO4. This is not a correct, that's not a correct equation because Ca, I would need to do, here I could do this, let's see. Let's do Ca, not do Ca, let's do Al. So Al is 3 plus, whereas SO4 is 2 minus. So that becomes Al2 SO4 3. Okay? So let's say we had that substance. What would I be for that? There are 2 Al ions. It splits apart into 2 Al ions, right? But this is all grouped together. That is a single polyatomic ion. So there's 2 of these, and there's 3 SO4s. Okay, so your total would be 2 plus 3 or 5. So I would be 5 for that. Good question. All right. If it's not an ionic compound, if it's a covalent compound, the I for that, just assume it's 1. Okay, because it's contained as a single molecule. All right. Any other questions? Sorry to bore you guys that were maybe already studied up on this, but I just wanted to make sure we went through some of those problems and gave you an opportunity to ask any questions. If there's any additional questions that you have, I've still got 10 more minutes here, or I can stay a little later if you've got anything that you want to ask me about outside of this. All right? You guys have a good one, and as always, email me if you've got questions.